Okay, so we're moving on to friction with static particles. So it's just adding in that extra dimension within the questions. A refresher that friction is at its maximum point when it's equal to mu multiplied by the reaction force at the point where friction is occurring. So mu being our coefficient of friction. We often say that when something is literally on the verge of moving or the point of moving, then it's in limiting equilibrium. So it means it's about to go out of equilibrium and it's reached its limit at which that can be the case. Friction generally is less than mu r if an object is not moving, and friction always acts in the opposite direction to where it would move. So were it to be moving to the right, then friction would be acting to the left. So we'll just go through these examples. So a mass of 8 kilograms rests on a rough horizontal plane. Okay. Rough horizontal, obviously the word rough implies that there is going to be friction. The mass may be modelled as a particle, and the coefficient of friction between the mass and the plane is 0.5. So I'm just going to write mu equals 0.5 down, just so I don't forget it when I'm working through the question. So find the magnitude of the maximum force P, which acts on this mass without causing it to move, if, and then we've got two separate questions. So P is a force that would be causing it to move forward, and therefore we have friction acting backwards. And obviously we've got the weight, 8g, and then we've got our normal reaction. So A is if the force is horizontal. So this is my part A, where the force is horizontal. So we need to work out what our normal reaction is first, before we can work out the value of friction, and then use this to work out the value of P. So I'm going to resolve vertically. Because there is no movement horizontally and there are no additional forces, then the normal reaction must be equal to 8g. So my friction, which is also equal to my force P, because it's without causing it to move, the maximum it can be without causing it to move. So we are assuming that friction has reached its max, and because they're not moving, they must be equivalent to each other. So that must be equal to 0.5 multiplied by 8g, which is 39.2 newtons to 3 significant figures. Okay. Part B says to calculate the same thing, so the magnitude of the maximum force P can act without causing it to move, given that P acts at an angle of 60 degrees to the horizontal. So that's now our force P. We still have our friction acting backwards. We've still got our normal reaction. We still have our weight, 8g. But obviously if we're resolving vertically and horizontally, then we're going to need to resolve this force vertically and horizontally as well. So we're going to resolve vertically first, so that we have a value for R. So R plus P sine 60 must be equal to 8g. So therefore R is going to be 8g. Subtract P sine 60. So that's all we can really do at the moment. R is reliant on an unknown, so we are going to need some simultaneous equations. I'm going to write down what friction would be equal to, because that's going to help us find P, because friction at its maximum would be 0.5 multiplied by this. Now I have actually put this into the calculator because I know it's going to be a third, but it's going to be relatively straightforward. So friction is 4g minus the root of 3 over 4 lots of P. So I'm now going to resolve horizontally. And this time I'm going to get that P cos 60 must be equal to friction. Now that I've got that, I have two items, both in terms of P, that are equal to friction. I'm just going to quickly simplify that because I know that cos 60 is half of P. So therefore, a half P is equal to 4g minus root 3 over 4p. And we can rearrange this and solve for P. So you're going to add root 3 over 4p to this side and then divide by that value. I'm not going to show you that kind of thing on your calculator. But therefore P is going to be equal to 42 newtons. So this one's slightly harder in that we get to unknowns. So that's fine. We quite often will have a number of unknowns, but usually if you resolve in the way that you need to, you'll end up with something that you can either cancel out one of the unknowns or you've got a pair of simultaneous equations that you can solve. Okay, so we'll go on to the next example. So a box of mass 10 kilograms rests in limiting equilibrium on a rough plane inclined at 20 degrees above the horizontal. So 20 degrees above the horizontal, got my mass of 10 kilograms. Obviously got my weight, 10g, acting down. There will obviously be a normal reaction. Now it says that it's resting on a rough plane. There's no force acting downwards, but we must have friction acting upwards, because naturally if there's no force, if it's resting, the only way that this item is going to move is if it's sliding down. So part A is find the coefficient of friction. So we're finding mu, okay? So we are going to resolve perpendicular and parallel to the plane. So obviously just want to draw in my parallel and perpendicular lines. That's 20. So I'm going to start by resolving perpendicular to the plane. So my normal reaction must be equal to 10g cos 20. And I'm going to leave it like that rather than writing a horrible decimal, because it's easy then to substitute that in. I'm also going to resolve horizontally. Now I've put my arrow down that way, just because if the movement's going this way, I've seen that as positive movement, but honestly it makes no real difference in this case. So 10g sine 20 must be equal to friction. So now I have a value for friction and a value for my normal reaction. So therefore, if I know F max is mu r, then I know that 10g sine 20 must be equal to mu multiplied by 10g cos 20. So all I'm doing is substituting in my values. Obviously going to rearrange this to find mu, so divide both sides by 10g cos 20, which actually ends up simplifying to tan 20, but this is 0.364 to 3 significant figures. Part B of the question says a horizontal force of magnitude P is applied to the box. So I'm going to redraw my diagram because it now is quite different. So my box is still acting at 20 degrees to the horizontal. Still here, I've still got my weight of 10g, and I've still got my normal reaction. The difference here is that I have a horizontal force of magnitude P applying to the box. So this means that movement would now be up the slope. As a result, friction is acting down the slope. So you can see actually my drawing is really quite significantly different. And the question says find the maximum possible value of P. So if I'm finding the maximum possible value of P, that means I'm finding the point, because it's where the box remains in equilibrium, that's the point where friction is at its maximum as well. So I've got to resolve parallel and perpendicular to the plane. And that includes this force P, because at the moment this force P isn't parallel perpendicular, it's acting horizontal, okay? So it's acting actually parallel to the ground, but we need it to be to the plane we're using. So we do need to resolve this as well. Now it's slightly more difficult to work out angles here, but if you imagined, if I drew a line down here, that this would be 70 degrees. So actually I might draw that to the side so that you can see. So that's my force P. If I were to do a line here, if I know that's 20, that angle must be 70. This must create a right angle because I've got a horizontal and a vertical line, so that angle there must be 20. So being able to visualise these angles in parallel and perpendicular lines is really, really quite important. Okay, so we're going to resolve perpendicular to the plane first. So I've got my normal reaction is my force going up, and that is equal to P sine 20 plus 10g cos 20. Okay, so I can't really do anything with that at the moment. So I'm going to resolve parallel to the plane. So the only thing I've got acting upwards, and actually I realise I've drawn my arrow the wrong way for P, because P is obviously an upwards force, so P is going that way. So P cos 20 is equal to 10g sine 20 plus friction. Okay, we can't forget that friction is there. Okay, now I'm going to make it F equals, because obviously I want to work out P in this case. I already have a value for mu, because I've got a value for mu from the previous question. The mu is related to the plane, it's not related to the situation. So I'm just going to make this equal to F. Now I'm going to go just back to this part here because I need to use this mu. And I want to do it as exact as possible. If I just use 0.364, I'm not going to get an accurate answer for my part B. Now I said before I didn't write it down. 10g sine 20 divided by 10g cos 20 means that mu must be equal to tan 20. And this is what I'm going to use to give me a more exact answer in part B. So I know friction is at its maximum, so I'm going to use F max equals mu r. So mu is the same from the previous question. So P cos 20 subtract 10g sine 20 must be equal to my value for mu, which is tan 20. So just put in brackets that it's mu to remind you. If you used 0.6364 and then a few other decimal places, that would also be fine. It's just that tan 20 actually is really easier to type in. And that is multiplied by my value for r, which is P sine 20 plus 10g cos 20. Okay? I obviously want to get P on its own. So what we've now got is actually just a complex rearrangement question. So I need to get P on its own. So I will go through these steps with you just to make sure that we haven't forgotten this from GCSE and we don't make any silly errors. So I'm going to take this over to the left-hand side. So I need to subtract 1020 multiplied by P sine 20 to this side. So P cos 20 subtract P multiplied by tan 20 multiplied by sine 20, and that is equal to, so I've still got tan 20 multiplied by 10g cos 20, but I've also added 10g sine 20. Now I could factorise this to make P equals so P is equal to tan 20, 10g cos 20 plus 10g sine 20 all over cos 20 minus tan 20 sine 20. So all I've skipped here is me going P brackets, so factorising this side. So therefore, P is equal to 82.2 newtons to 3 significant figures.